Hello everyone, welcome to my poster presentation. My honors project is a literature review on the different methods of detecting exoplanets. Let's start by defining what are exoplanets. They're simply planets that are orbiting around other stars than our Sun. To be included in the NASA Exoplanet Archive, an object must meet the following criteria. 1. The mass is less than or equal to 30 Jupiter masses. 2. The object is not free-floating. And 3. The findings and the observations are peer-reviewed. For example, the companion to the red dwarf SCR 1845 is not an exoplanet because its estimated mass is larger than 30 Jupiter masses. Finding exoplanets help us understand better our own solar system, especially the way how the planets are formed. Also, we're looking for other possible habitable worlds as we can live on Earth forever. Many methods are available to detect exoplanets. In this presentation, I will talk about 4 of them: transit photometry, radio velocity, direct imaging, and astrometry. The order is in decreasing number of exoplanets discovered using that method. Transit photometry is a method where a detector is used to measure the level of light of a star over a period of time. It is the same idea as the solar eclipse. As an object travels between the star and the observer, the object blocks a little amount of light, causing the star to become dimmer. And when the object gets out of the way, the brightness of the star goes back to normal. The graph created when plotting the data is called a light curve, which has the shape shown on the right. With 3,323 exoplanets discovered, the transit method is the most effective one for detecting exoplanets. Here's a video explaining the transit method. You can see the light curve on the bottom left corner. This is a planet orbiting around the star. As it passes in front of the star, the brightness lowers, and then it goes back up when the planet is gone. And it goes on, repeating the pattern when the planet partially blocks the star. This method also allows us to get valuable information about the detecting exoplanets, such as their size, their distance from the star around which they're orbiting, and their atmosphere composition. The size can be determined by looking at the light curve. A bigger object blocks more light, creating a deeper light curve. As planets orbit around the star, they take more time to make a full cycle if they're further away from the star, and less time if they're closer. So by looking at the time of the event, we can tell how far the planets are from the stars. And finally, when a planet travels in front of the star, some starlight passes through its atmosphere. Scientists can then analyze the color of the light to have an idea of the atmospheric composition. The next method is called radio velocity. The idea is that the exoplanet also exerts a gravitational force on the star, causing the star to move around as shown in the picture. It is a tiny movement since the star is much more massive than the planet. Of course, the picture representation is exaggerated. The mass of the planet can be determined by looking at how much the star moves due to the gravitational force, as a heavier object creates a stronger force. Nevertheless, the star's movement is too small to be easily observed. Instead, Doppler shift is what we are detecting. When the star moves away from us, the light emitted is set to redshift. On the other hand, the light blue shifts when the star moves towards us. So far, 833 exoplanets have been discovered using the radio velocity method. It is also used to confirm the planets found with other methods. Now here is a video. Again, a planet is orbiting around the star and the star is also moving. The light wave is shown below. Notice the red shift as it moves away and the blue shift as it comes towards us. Here is an example where both the transit photometry and the radio velocity methods are used to obtain information about the structure of exoplanets. The Characterizing Exoplanet Satellite is a mission searching for the transits on bright stars already known to host planets having a mass between super-Earth and Neptune. That means the ratio of mass planet over mass Earth must be between 1 and 20. The mass is determined using the radial velocity technique, but this is already provided and it is not part of this mission. The radius, however, is found by transit measurements done by this satellite. Then, the mass-radius relation can be used to determine the density of the planets, which can tell a lot about the composition. For example, a planet with 5 times the mass of Earth, having 50% of solid terrestrial composition and 50% of water vapor, has a radius approximately twice as large as a planet of the same mass, but with 100% terrestrial composition. Paired with other parameters, such as the distance from the host star and the temperature, CHEOPS can identify planets having a significant atmosphere. Direct imaging is a pretty simple concept. It is just taking pictures of the exoplanet. However, the challenge is that the host star is millions of times brighter than any light reflected off the planet or the heat of the radiation of the planet itself. The solution is to block the starlight and seek for planets that are far away from the star. Similarly, when you look at the stars at night, you want to block the street lamps. Two methods can be used to block the starlight. The first one is called coronagraphy. The device is used inside the telescope to block the starlight before it reaches the detector. This method is used for ground-based telescopes. And the second one is built for the space-based telescopes. It is a star shade that positions itself to block the starlight before it even enters the telescope. The star shade is a separate spacecraft placed at the right distance and the right angle. Direct imaging is a very nice method because it gives an image of the planet itself. Studying the image can provide the temperature, the presence of water vapor, and other useful information. So far, 51 exoplanets have been detected using direct imaging. The video here shows the idea of blocking the starlight. We have the super bright star on the right, and when it is blocked, we can see the planet just beside the star. The last method is called astrometry. Just as the radial velocity method, it uses the fact that the planet also exerts the gravitational force on the star, which moves around. However, astrometry doesn't look at the Doppler shift. Instead, it evaluates the position of the star compared to its nearby stars over a period of time. As expected, this method is incredibly hard because of how tiny the movements are. It is very difficult to detect them, especially when the exoplanets are small, like the size of the Earth. It is even more challenging to use this method from the surface of the Earth because the atmosphere can distort light. And this is probably why only one exoplanet has been discovered so far using astrometry. And another video. As you can see, it is still based on the fact that the star is influenced by the exoplanet. Astronomers take pictures of the sky for a period of time and observe the positional differences between the stars. In this video, 3 lines are drawn to show the variation of the distance between the target star and the neighbor stars. In conclusion, over 4,000 exoplanets have been detected and confirmed, and thousands of other candidates are still waiting for further observations. The most effective methods are transit photometry and radial velocity. They are excellent for finding exoplanets that are fairly close to the host star. On the contrary, direct imaging works well for far and bright planets, such as young planets emitting heat of formation. It is also the only method out of the 4 presented that doesn't rely on the host star to find planets. Astrometry is currently very challenging to use with the technology we have, but it could become more useful in the future as we upgrade the equipment. As more and more exoplanets are being discovered, we can start focusing more on detecting possible signs of life on those exoplanets. If successful, it will surely tell us more about the evolution of life. And a crazier idea would be to find a way to travel to an exoplanet that is considered habitable, since, just as I mentioned at the beginning, it is impossible to live on Earth forever. Thank you for listening.